All right, welcome in junior devs to a very special explainer session. Today, we are targeting an absolutely massive mainframe. I'm talking about the Cambridge AS and A-Level Mathematics 9709 exam. And specifically, we're hacking the functions module. You know, the difference between walking away with a B and securing that elusive A-star in mathematics, well, it doesn't just come down to memorizing a bunch of formulas. It comes down to treating an essay or one of those really complex multi-part problems exactly like an algorithm. Think about it. It requires strict syntax, flawless structure, and perfect execution. If you've been struggling to bridge that gap, if you feel like you're stuck and just can't secure those top-tier marks, you're exactly where you need to be. We're going to treat this entire explainer like the ultimate Silicon Valley exam hackathon to completely optimize your mathematical code. So let's boot this up and dive right in. So here's the core question we need to crack. Why do students find evaluating evidence and drawing conclusions so incredibly hard in a pure math paper? It's a fascinating problem, really. A lot of candidates, maybe even you at times, view math as just this race to find the number. Get to the end of the equation, circle the answer, and you're done. But Cambridge examiners, they look at it totally differently. They view your exam as an algorithmic problem that needs a precise, logical step-by-step solution. You are literally being tested on evaluating alternatives, comparing different approaches, and making heavily justified recommendations based on the data you're given. And honestly, if your mental code is buggy, your final answer is just going to crash the whole system. To fix those bugs, we are initiating a strict system boot sequence today. Here is the exact roadmap we're following. First, booting the system. Second, debugging the command matrix. Third, compiling the patch. Fourth, hitting the beta testing arena. And finally, step 5, code deployment. All right, initiating phase 1, booting the system and looking at our core principles. The entire syllabus is built on one underlying truth that you absolutely must understand. Top-performing students, the ones getting those top marks, they exhibit a deeply connected conceptual understanding that they can transfer to entirely unfamiliar, weird contexts. You just can't rely on knowing a formula anymore. You really have to understand the underlying architecture behind it. Let's break down the foundational parameters of our mathematical code by looking through the functions framework. Think of these 5 concepts as your core non-negotiable variables. First up, domain. This is simply the set of all your possible input values. Then you have range, which is the set of all possible output values that your function can actually produce. Next is one-to-one. This is a super strict rule where every single output has exactly one unique input. And listen, that is absolutely essential for our next variable, the inverse, to even exist. The inverse is basically reversing your algorithm to get right back to your original input. And finally, composition. This is where things get fun, feeding the output of one function directly into another as its new input. These precise definitions, and more importantly, how they cause and react to each other, that forms the entire theoretical framework of your exam. To really grasp how Cambridge actually grades your understanding of these terms, I want you to imagine 2 hypothetical coders taking this exact exam. First, we have Dev Alex. Now, Alex provides excellent raw data inputs, like knows every equation in the book by heart, but Alex causes major memory leaks due to really poor analysis. Alex basically just writes down everything they can possibly think of, praying for a stray mark, but they stay entirely stuck in the descriptive cognitive domain. No depth. Next, we have Dev Sam. Now, Sam is different. Sam has great logical loops and real analytical depth, but Sam constantly fails syntax precision rules, like totally forgetting domain restrictions or just leaving out proper mathematical notation. You see, the examiners are targeting distinct cognitive domains here: knowledge, application, and analysis. And right now, both Alex and Sam are completely failing to hit the peak of that framework. Moving into phase 2, debugging the command matrix to clear the firewall. Listen, if you want those A-star marks, we have to map out a pseudocode outline that bypasses what I like to call the strict examiner firewall. This firewall is designed to automatically block and penalize buggy, disorganized, or lazy answers. And to understand what we're up against, we need to look at a very specific number: 3. There are exactly 3 critical examiner warnings that we've pulled straight out of the Cambridge Principal Examiner reports regarding this exact functions module. So your absolute priority is avoiding these top 3 system errors because they will cause instant, painful mark deductions. Error 1, forgetting proper format. This means losing incredibly easy, straightforward marks just because you didn't clearly state the domain for an inverse function. It's a rookie mistake. Error 2, ignoring presentation checks. Cambridge demands strict conventions, guys. We're talking proper headings, correct terminology, and clear, legible annotation. If your working out is a tangled mess, the examiner literally cannot parse your logic, and they won't give you the benefit of the doubt. And error 3, generic answers lacking specific context. This is a big one. The academic benchmarks prioritize analytical depth way over superficial breadth. You absolutely cannot just regurgitate a textbook definition you memorized. Your answer has to apply to the exact specific parameters of the question in front of you. In fact, the Cambridge Principal Examiner Report issues a very direct, undeniable warning about this. They state, and I quote, "The classic mistake is providing generic answers not specific to the question context. Always link every point to the given scenario." End quote. I want you to consider this an absolute fatal system error warning. Think about it. If you are analyzing a composite function model of a real-world scenario, your variables actually mean something physical. Your math script will fail compilation if you do not link every single mathematical step directly back to the physical scenario that the question presented to you. Do not be generic. Let's move into phase 3. Compiling the patch and looking at method mark algorithms. We really need to upgrade our core methodology to secure what we call the method mark strategy. You see, Cambridge doesn't just blindly grade your final output. They actually award points for the mathematical process itself. You can secure massive points just by showing the examiner that your algorithm is running correctly, even if some silly minor arithmetic bug alters your final string at the very end. Okay, quick system pause. Before we push this final patch to secure those maximum marks, I need you to optimize your system feed right this second. Hit that subscribe button for Ace the Exams at the handle @AceTheExams, and make sure you turn on all notifications. We are deploying weekly system updates to keep your academic hardware running flawlessly, and believe me, you do not want to miss the next masterclass we drop. All right, we are back online. Let's deploy the method patch. When you are staring down a massive multi-part math problem, you need a precise data interpretation sequence. Step 1, extract data from texts and tables. You need to identify your domain constraints immediately, right out of the gate. Step 2, interpret relationships. Ask yourself, is the function 1, 1? How does that specific fact impact the inverse? Step 3, draw evidence-based conclusions. You have to connect the dots. The principal examiner reports specifically, explicitly highlight that candidates who reference cross-topic connections achieve significantly higher marks than those who don't. Now, if you ever find yourself totally stuck on a logic error mid-argument, I want you to deploy the Peel syntax. Now, I know what you're thinking. Isn't Peel traditionally an English or history essay framework? Yes, but it is an absolute game changer and an incredible bug fix for higher-order math reasoning, too. Point, clearly state the mathematical terminology or the heading. Evidence, extract the specific data or equation straight from the prompt. Evaluation, compare approaches. For instance, show the examiner why one domain restriction works perfectly while another one totally fails. Link, tie it directly back to the specific context of the question. Wrapping your math in this structure guarantees your reasoning meets those highest evaluative levels the examiners are looking for. Welcome to Phase 4, the beta testing arena. It is time for some interactive reader audits to really put your real-time error detection skills to the test. Let's see what you've got. So, if we were to run a trend extraction on your cognitive domains right now, where do you think you'd land? If you just describe the shape of a curve, well, you're stuck down at level 1, descriptive. Now, if you actually calculate the exact intersection points, okay, great, you've hit level 2, analytical. But to reach the absolute peak, level 3, evaluative, you must compare approaches. You have to use comparative connectives, and you have to mathematically justify why a specific domain restriction is absolutely necessary for the inverse to even exist. Getting to that evaluative stage is the ultimate peak of the Cambridge Assessment Objective Framework. Let's do a quick code review to prove this. Picture a buggy, generic output from a student. It's poorly formatted, it has zero clear annotation, and it uses completely incorrect terminology. It just lazily says x is greater than 0 with absolutely no context. Now compare that in your mind to an optimized output. It is context-specific, perfectly annotated, and uses precise terminology. It says something like, since the function is a quadratic model for distance, we restrict the domain to x is greater than 0 because time cannot be negative, thus ensuring the function is 1-to-1 and an inverse exists. Do you see the massive difference there? That first answer crashes hard at the examiner firewall, but that second one, it compiles perfectly and secures full marks. And that brings us to phase 5, code deployment and our final architecture. We have reached the final sprint of our hackathon. We are going to lock in the final, high-scoring, optimized text string to ensure you meet maximum academic benchmarks on your next paper. To ensure you literally never face a memory leak during the stress of an exam, I want you to install this cheat sheet architecture memory hack right into your brain. It's an acronym, DROIC. Domain, range, 1, 1, Inverse composition. Whenever you sit down and see a functions question, I want you to physically write DROIC at the top of your page. Then ask yourself, have I checked the domain? Have I found the range? Is this function 1, 1? Can I actually find the inverse? Does it require composition? Let this acronym be the master loop that guides every step of your algorithmic thinking. And right before you hand in that paper, you need to make your final commit. Ensure you have checked off these 3 absolute guarantees. Number 1, have you applied strict conventions using proper mathematical headings and crystal clear annotation? Number 2, have you highlighted cross-topic connections, maybe integrating your functions knowledge with quadratics or even trigonometry? And number 3, have you fully justified your mathematical recommendations with solid, context-specific evidence? If you hit those 3, your code is clean. And with that, system upgrade complete. Junior devs, your mathematical architecture is now incredibly robust. To ensure you maintain this high level of performance, subscribe to @ACEDExams right now. Click that bell icon so you don't miss our weekly updates. And hey, I want you to comment your specific subject and exam level down below so we know exactly what module to hack for you next. Go practice those past paper questions immediately so you can solidify this patch in your memory. I'm going to leave you with this final thought to ponder as you log off today. Have you truly optimized your exam code, or is your very next paper doomed to crash and burn at the examiner firewall? Take this algorithmic mindset you just learned, apply it to your very next practice paper, and watch your grades compile straight into A stars. Happy coding, everyone, and we'll see you in the next explainer session.